Hello, this is part C of the Chapter 5 lesson. In part C, we're going to continue talking about probability, but we're going to talk about calculating probabilities in a different way using what we call distributions. Part C, we're going to talk about one specific distribution called the binomial distribution. Part D, we're going to talk about another distribution called the normal distribution. Now, starting in this section, we are going to be using the Excel workbook titled Chapter 5 to do the calculations. We're not going to build this workbook from scratch. I've already built it. We're just going to be modifying individual cells in order to do the calculations. So get that out and ready to go when needed. You can also use that workbook to do all the calculations for the homework problems. Now, one thing we might note in our previous two parts of this chapter is that when we calculated probabilities, we used it based on data. We had data from our entire population, and we used that data to calculate probabilities by taking the number of people in our population with a certain characteristic and divide it by our total population size. But the problem is that we don't always have data that we can use to calculate probabilities. So we need a different type of formula for calculating probabilities. These formulas are generically called probability models, or also called distributions. And we're going to talk about two specific distributions, the binomial and the normal distribution. So to introduce to define the binomial distribution, this type of distribution describes a scenario that meets the following requirements. Number one, we have a fixed number of trials. Now, a trial is some sort of activity that we do over and over again, like flipping a coin or rolling a die. Number two, the trials are independent. Independent means that what happens in one trial has no effect on any other trial. Number three, each trial has only two characteristics, commonly called success and failure. And this is where the bi in the binomial distribution comes from. The success doesn't necessarily mean that something bad happened, or good happened, excuse me. A success simply means that we observed whatever it is we're interested in. Nor does a failure mean that something bad happens. A failure means that we didn't observe whatever it is we were interested in. And then the fourth requirement is kind of technical. The probability of a success remains the same in all trials. So in a binomial distribution, we got a number of trials, everything's independent, and we have two characteristics. So to illustrate this, let's look at a couple of scenarios. First example, a couple plans to have 5 children. So we could think of each trial or each child as a trial. So we have 5 trials. They're independent in the sense that we'll assume that the gender of one child has no effect on the gender of any other. Each trial has only two characteristics. They're either boy or a girl. We'll call a success a girl and a failure boy. Again, not saying that one is good and the other is bad. It just means that in this case we're interested in girls. And fourth, we'll assume that the probability of a success or the probability of a girl is 1/2 in all trials. So this scenario can be described by a binomial distribution. Another example, suppose that 4% of all people who have a heart attack die from the heart attack. And suppose that we study 50 patients who had a heart attack. So we can think of each person as a trial. So we have 50 trials. They're independent in the sense that what happens to one person has no effect on any other. Each trial has only two characteristics. Either the person dies or they don't die. We'll call a success not dying and a failure dying. So the probability of a success is 0.96 in all trials. Because 4% of people die, that means that 96% of people live. And so this scenario can be described by a binomial distribution. Well, let's look at some questions that we might ask in these different situations. Number one, first scenario, we might ask, what's the probability that the couple has exactly 3 girls? Second scenario, we might ask, what's the probability that exactly 4 out of the 50 patients die? Or in general, these questions have the form, what is the probability of X successes? In the first question, it was what's the probability of 3 successes. In the second, what's the probability of 4 successes. So those are the types of questions that we want to ask in a scenario involving a binomial distribution. And the binomial distribution allows us a formula, or gives us a formula for calculating these probabilities. So here's the formula that we're going to use to calculate these probabilities. So we need 3 variables that we need to define here. N is the number of trials. X is the number of successes that we're interested in. X has to be between 0 and n. And then P is the probability of a success in one trial. And a formula for calculating the probability of X successes is given by this rather scary looking formula. This is read n factorial divided by n minus x factorial times x factorial times p to the x times 1 minus p to the n minus x. Now real briefly, let's talk about this factorial. A factorial is defined for whole numbers. And so, for instance, 5 factorial is defined to be 5 times 4 times 3 times 2 times 1. 2 factorial is 2 times 1. In general, k factorial is k times k minus 1 times k minus 2. We keep going down all the way to 1. And then 0 factorial is defined to be 0. So let's look at how we could use this formula. Now, in the end, we're going to let Excel do the calculations, but let's illustrate how we could use this formula to do the calculations. This is example 5.9 from the textbook. Medication for allergies is effective in reducing symptoms in 80% of patients. If medication is given to 10 patients, what is the probability it is effective in exactly 7? Okay. So let's make an observation here. Let's call a success a patient with reduced symptoms. That's what we're interested in. And so we give the the medicine to 10 patients. Each patient is a trial, so we have 10 trials. The probability of a success is 0.8 because the medication is effective in 80%. And so this scenario is described by a binomial distribution. We want to know what's the probability of exactly 7 successes. So we can calculate this probability of 7 successes with our formula. 10 factorial, 7 factorial, 10 minus 7 factorial, 0.8 to the 7, 1 minus 0.8 to the 10 minus 7. We do that arithmetic and we get 0.2013. So that's how we could use that formula to calculate the probability of exactly 7 successes. But as we see, this formula is a little bit complicated to use. So we've built this formula into this workbook, chapter 5. So if you go to, there's several different worksheets in that workbook. If you go to the worksheet binomial, you'll see some cells that look like this. And so in these cells, in these workbooks that I have built, the cells in yellow are cells that we can change. The cells in green are automatically calculated by Excel. So in this case, we have n equals 10 successes, p is 0.8, and x is 7. If we just enter those numbers, hit enter, Excel will automatically calculate the probability of exactly x successes, which is the exact same. So it calculated 0.2013, which is the exact same thing we got using the formulas. Okay. So let's go back to this, or work with the same example, but ask a slightly different question. What's the probability the medication is effective in 5 patients or less? So we're not interested in just exactly 5 patients. We're interested in 5 or 4 or 3 or 2 or 1 or 0. And so we could calculate it in this way. We could find the probability of exactly 5 successes, and then exactly 4, and then exactly 3, and exactly 2, and exactly 1, and exactly 0, and then add those 5 probabilities together. Whenever we see the word or, that indicates that we add probabilities. So we could calculate the 6 different probabilities using that formula, add them together. But luckily we've got this formula for calculating this built into the Excel workbook, Chapter 5. And again, we got the same values of n, p, and x up here. But now what we want is the probability of 5 successes or less. So we're going to look at this cell right here. And so that calculated all 6 of these probabilities, added them together, and there we get our probability. So our solution is 0.0328. So about a 0.3 or a 3% chance of getting success in 5 patients or less. Now let's make an observation here about this scenario, that the number of patients with reduced symptoms is a discrete variable. Remember in last chapter we defined a discrete variable to be a variable that has simply a finite number of possible values. So in this case we could have either 0 patients with reduced symptoms, or 1, or 2, all the way up to 10. There's only a finite number of values. And so for this reason the binomial distribution is called a discrete probability model. The normal distribution that we'll talk about in the next part of this chapter deals with continuous variables, so it's called a continuous probability model. So let's look at another example of calculating binomial probabilities. An antibiotic is claimed to be effective in 70% of patients. If the antibiotic is given to 5 patients, what is the probability it is effective on exactly 3? Well, let's call a success a patient in which the antibiotic is effective. And so we can think of each of our 5 patients as a trial. In each patient, the antibiotic is either effective or not. So we have 2 outcomes. We'll assume everything is independent. The probability of a success is 0.7. And so we're dealing with a binomial distribution with 5 trials and a probability of a success in 0.7. We want to know the probability of exactly 3 successes, and so we could plug the values of our numbers into our formula for the binomial distribution, do that arithmetic, and we get our answer. Or we could go back to that workbook, Chapter 5, change the values of n, p, and x, and calculate the probability of exactly 3 successes to be the same thing that we just got over here. Okay. Well, now let's modify our question a little bit. We might ask, what's the probability that the antibiotic is effective on at least 3 of the patients? So at least 3 means 3 or 4 or 5. And so we could, in principle, calculate these 3 probabilities using the formula, add them up, and we get our probability. But we don't have to do that. That formula is built into the workbook. Again, we enter n, p, and x, and we want the probability of 3 successes or more. That's the same as saying at least 3. And so that gives us our answer there. It calculates these 3 probabilities, adds them up, and we get our answer, 0.8369. Now, with a binomial distribution, we can calculate something that we call the mean or the expected value. And it's denoted mu, and it equals n times p. Now, what does this number mean? Well, we could think of it as the expected number of successes in the n trials. So as an example, let's go back to this allergy medication, where a success was a patient with reduced symptoms. We had 10 trials, probability of 0.8. And so if we calculate mu, 10 times 0.8 is 8. And so this means that we expect 8 out of 10 patients to have reduced symptoms. Doesn't mean that we will get exactly 8. It's just a theoretical number. If we look at the antibiotic example, a success is a patient in which the antibiotic is effective. We had 5 trials. Probability of a success is 0.7. And so the expected value is 5 times 0.7, or 3.5. So we would interpret this by saying that we expect the antibiotic to be effective in 3.5 out of 5 patients. Again, this is not something that we actually expect to observe. It's just a theoretical number. We can't have exactly 3.5 successes The number of successes has to be a whole number. Again, this is just a theoretical number.